Okay, before we get started with talking about computers and everything, let's go back to the first things that you have probably ever learned, and that is how do you do math? So we have two numbers, 5 and 7. How do we add them? Well, we can just put them vertically like this, and then we have 2 here. Since 12's the answer is too big to fit with just one digit, we carry the 1 over to the tens digit, and we just put it here, and the answer is 12. For some bigger numbers like 15 and 17, we do basically the same thing too. We carry the 1 over, and now you don't only add the tens place, but you also include the carry along with it, so the answer is 32. This pattern can continue endlessly for as long as you want, and this is essentially how computers do it with binary in the exact same way. Okay, but what about negative numbers? Let's say we have a positive 7 written like this. Negative 7 in normal mathematics will just be represented by a negative sign in front. So for example, we add 7, 5, both positive. This will obviously give you positive 12 like we have said before. And when you add negative 7 and negative 5, it also gives you negative 12. So what you might think as a rule is you just keep the sign like this. But what about if you are adding a negative number with a positive number like this? What if it's 7 and negative 5? Well, this is a little bit complicated because you can't just say it's 12 and then you decide whether it's positive or negative, because it's neither of those. The actual answer will just be positive 2. So it looks like there's two different rules, one for when you're dealing with the same sign and one for dealing with different signs. But a good way of thinking of all of this is basically using a number line. So positive would just mean to go to the right, negative would just mean go to the left. So when you add two numbers, you're saying go this much, and then from that place, go another distance. So for example, positive 7 plus positive 5 can be just written as this, and when you count the total distance, that would be 12. Negative 7 on the other hand, and then negative 5 will also be negative 12 because you're moving 12 units to the left this time. And when you're adding something, when you're adding a negative and a positive, you just go right a bit and then you go left a bit. And the distance here would be something like 2. And that is how you can incorporate additions of negative and positive at the same time. And this also means you can do subtraction, because really subtraction is just the addition of a negative or the reverse. So this is really useful, but however, you have to still remember basically two different rules of going to the left and going to the right. Now in mathematics, the number line of course goes all the way forever to the left and the right. It extends infinitely in both directions. You can have, for example, 1 million, 1 trillion, 1 quintillion, negative 1 million, etc., whatever you want. However, if you were to actually write this, eventually you will run out of space, right? You and the computer, and if you're writing on paper, you can only write a certain amount of digits before you just run out of places to run. So what happens after there? Let's say you have only place to write 3 digits, right? Let's say you have you can write 0, 0, 0, you can write 100, you can write 200. The biggest number you will ever be able to write is 999. So what if you try to add 1 to that? Normally this would just be 1000, right? However, you don't have 1000. So a good and lazy way to deal with this is just chop the 1000 off. So 999 plus 1 in this case would just be 0 again. And while this seems like a glitch, it's actually really useful in storing data. Instead of having a number line, you basically have a circle. So when you go big enough, it just suddenly snaps back. It's not great to think of it as a circle. You should probably think of it more as just like it jumps back. So after it goes for a while, it just instantly goes back. However, circle also works decently well in this situation. So this is what we call overflowing. This property with overflowing actually gives us some very interesting things we could do. Let's say you have the number 3, which on this circle we should say maybe mark it like somewhere here. Well, if you want to add 1, we can just make it equal to 4, right? So that is very simple. You just go forwards a little bit to 4. If you want 4 to subtract by 1, right? Maybe you just want 3 minus 1. What you do is, one way you can do it is just go back. But you might notice that on a circle, another thing you can do is just go all the way around till you cycle back and just before it closes. And what that is essentially called 3 plus 9. And if you think about this, this works perfectly. You get 12, except the first digit is in the tens place, it is stored because you can't write 2 digits. And then you get 2. If you add 9 again, you get 1. If you add 9 again, you will get 0. So now you might be thinking, what happens if you add 9 again? Well, this time you just get 9. You can't have a negative number after all because there's nothing that you can write a negative sign at. So when you add 9, like, is this our rule broken? Well, don't consider it as like a broken rule, but consider it as something that's pretty valuable. Now you can say that 9 represents negative 1. This is equivalent to meaning negative 1. So if you do 9 plus 9 again, you get 8. You do that again, you get 7. You do that again, you get 6. And then again, it's 5. And here, in front of that would be 4. Plus 9 equals 3. So now you see we have a chain with 4 being the biggest number there is, and 5 being the smallest number. So 5 would actually represent negative 5. This would be negative 4. This would be our representation of negative 3. This is negative 2. This is negative 1. This is 0. And this would be just 1, 2, 3, and 4 as is normally as it is. You might look at this and feel like it is very confusing and is way more complicated than it should be, but this actually has some really great advantages. Namely being that you can add, subtract, and negative and positive numbers in the exact same way. So let's say we do 1 plus 2 equals to 3. This is basically all we are doing. This is the exact same thing. 1 means 1, 2 means 2, 3 means 3. This works perfectly. What if we want to do negatives? So by negatives, the adder has no concept of negative. It's just adding 9 and 8, which would give you 7. But if we look it up to what 9, 8, and 7 corresponds to, well, 9 is negative 1, right? Negative 1 plus negative 2 equals to, what is it equal to? Negative 3. This works perfectly well as well. So what if we want to do a negative number plus a positive number? Let's say we want to do 2 plus negative, I don't know, negative 3. What this is basically is this 2 plus 7. And 2 plus 7, if you give that to the adder, it would give you 9. And what does 9 represent? Well, 9 represents negative 1. So you have just calculated 2 plus negative 3 equals to negative 1 perfectly. And the system doesn't even know that the negatives exist. It is just thinking that you are doing 2 plus 7. But if you translate it back into negatives, everything works really well. And this is one of the genius parts about this mechanism. So now let's look at binary. In the normal mathematical way, for example, 0 will just be 0. 1 is just 1, but there's no digit 2. What you do is basically add 1 to the 2's place and then go put 0 here. So this is actually a representation of 2. And we call it 1, 0. 3 will be this, and 4 will be this, and 5 will be this, and you can see the pattern. Basically, whenever you add 1, if there's a 1 here, you carry it over to the next place. And 7, that's 6, and this would be 7. And in the same mathematical way, we can basically write negative numbers and positive numbers like this, for example, by adding a negative sign. And of course, when you're storing it as bits, you can just say, for example, the first bit will always mean negative and positive, and the rest would be the number. For example, 0, 1 would be positive 1, 1, 1 would be negative 1. But this is the same thing as I have talked about in the beginning about like positive 4 and negative 4. There's a lot of problems when you try to add these two. You had to basically write like special cases or at least 2 different scenarios of handling this. So we can use the same clever situation as adding 9 as before. And basically, as you notice, 9 is the biggest digit that there is. And we were talking about 1-digit numbers when we were talking about decimal. But let's say we want to subtract 1. Let's say in the decimal thing, we can now store 2 digits. And we want to get 27 to 26. Well, what we can do is not add 9, but add 99. So this will actually be 126. So that will just chop the first one off and you get 26. But basically here, instead of adding 9, because that doesn't exist, you add 1. So if there's 2 digits, you actually add 1, 1. 2 digits is a little bit small for this demonstration. Let's say we have 3 digits. what you do is if you were to add 1 to this, right, plus 1, you get 1, 0, 0, 1, then you get 0, 1, 0, 0, 1, 1, like that, right? You add 1 each time, like here. What if you want to go back down the negative way? Well, for this, instead of adding 9, you add 1, 1, 1. So you add 1, 1, 1 to that. Of course, 0 plus 1, 1, 1. That would just be 1, 1, 1. So if you add 1, 1, 1 to 1, 1, 1 again, what would that do? Well, let's set up a addition thing. So this would be 0. And now since there's 1, 1, 1 like that, well, there's 3, so there will be 1 here. And then you carry it over, and there will be 1. So this will just be 1, 1, 0. And you can continue going like that. So the next one would be 1, 0, 1 if you keep adding 1, 1, 1. And this would be 1, 0, 0 finally. If you add another 1, 1, 1, of course it would just go back to 0, 1, 1. So this can be represented in our decimal. So this is a representation of 0. This is negative 1. This is negative 2. This is negative 3. This is negative 4. This is positive 1. This is positive 2. And this is positive 3. And that's all of the digits and the numbers you can represent. Well, this method is called 2's complement, and it is basically the way of storing positive and negative integers in all programming languages. So how do you find the negative version of a positive number, which you would need to do in, for example, subtraction or something like that? Well, in normal mathematics, right, you can just say 4 and then you can do negative 4 or something like that. However, in our system, let's say for the decimal thing, the negative 4 is actually represented by 6, which you basically is not very clear how to get there. And I'm not going to be going into decimal now because in binary there's actually a very elegant solution. So let's say you have a number like I don't know, 0, 1, 1, that is 3, right? This is a representation of 3. To find negative 3, all you need to do is flip each of the bits. So you just say 0, 0, 1. But this is negative 4, as you remember. So to get negative 3, you actually add another 1 here. So you add 0, 0, 1 here. So negative 3 will always be 1.